Hi, I'm A.Maro. I'm a student of Industrial Engineer at the UTCH BIS, and this is a video about physical and chemical processes, physical changes, and their operating conditions. The first one is filtration. Filtration is a process that separates solid particles from liquids or gases by using a porous barrier. This process is used in many applications, such as wastewater treatment, coffee making, and scientific analysis. In wastewater treatment, filter materials with varying porosities and structures are employed to remove contaminants, ensuring clean effluent. In coffee making, paper filters trap coffee grounds, allowing only the flavorful liquid to seep through. Filtration also plays a vital role in pharmaceutical manufacturing, where sterile filters devoid of any microorganisms are mandatory to maintain product integrity. The food and beverage industry relies on filtration to enhance the quality of products. For example, winemakers use filtration to remove residual yeast after fermentation, ensuring a clean and refined wine. Moreover, in air purification systems, HEPA filters effectively capture airborne particles, enhancing indoor air quality and safeguarding human health. And the operating conditions of filtration, as the parameters include pressure, which can range from a few pounds per square inch (psi) for simple gravity filters to hundreds of psi for industrial processes. Filter pore size varies greatly, from micrometers to nanometers, depending on the particles to be removed. Flow rate, measured in gallons per minute or liters per hour, determines how quickly the filtration occurs. Distillation. Distillation is a process that separates different components of a liquid mixture based on their boiling points. This process is used in many applications, such as petroleum refining, alcoholic beverage production, and pharmaceutical manufacturing. In petroleum refining, crude oil undergoes fractional distillation, separating it into various products like gasoline, diesel, and jet fuel. In alcoholic beverage production, distillers meticulously control temperatures to extract specific flavors and aromas, resulting in a diverse array of spirits from delicate gins to robust whiskies. In the pharmaceutical sector, distillation purifies drugs and compounds, ensuring medicines meet stringent quality standards. Distillation can be classified into two types: batch distillation and continuous distillation. Batch distillation is used when small quantities of a product are required. In this process, the liquid mixture is heated in a still until it boils. The vapor is then condensed and collected in a separate container. Continuous distillation is used when large quantities of a product are required. In this process, the liquid mixture is fed into a column where it is heated and vaporized. The vapor rises to be removed through the column and condenses on trays or packaging material. The condensed liquid is then collected in a separate container. The operating conditions of distillation are that it occurs under controlled temperatures and pressures. For instance, in the production of ethanol, the mixture is heated to around 78.37 Celsius degrees at atmospheric pressure. Specific distillation methods like vacuum distillation allow for lower temperatures, which can preserve heat-sensitive components. Distillation columns, after several meters tall, enhance the separation by providing more surface area for condensation. Crystallization. Crystallization is a process that transforms disordered solutions into ordered structures. This process is akin to nature's artistry, where chaos is transformed into elegance. Sugar crystallization, a staple in kitchens worldwide, epitomizes this enhancing process. As a sugar solution cools, individual molecules come together to form beautiful crystals that are pleasing to the palate. Beyond the culinary realm, crystallization permeates industries, from purifying salt for consumption to synthesizing complex chemicals. In the pharmaceutical sector, crystallization is used to refine drugs, ensuring that patients receive pure and potent medications. Material scientists use crystallization to create advanced materials by tailoring crystal structures to engineer properties like strength and conductivity. Nature itself showcases the mesmerizing beauty of crystalline structures in the form of snowflakes and gemstones. Crystallization is an intricate interplay of temperature and molecular bonds that orchestrates the symphony of solids, making it a cornerstone of scientific wonder. Crystallization is not limited to human made processes, but also occurs naturally in various forms. For instance, snowflakes are formed when water vapor condenses on dust particles in the atmosphere and freezes into ice crystals. The intricate patterns of snowflakes are determined by temperature and humidity conditions during their formation. Similarly, gemstones are formed deep within the Earth's crust under high pressure and temperature conditions. The beauty of these natural crystals has captivated humans for centuries. Operating conditions are that they include cooling rate, which affects crystal size and purity, supersaturation, achieved by dissolving more solute than the solvent can normally hold at a specific temperature, is essential for crystal formation. Stirring or seeding, seeding the solution with existing crystals provides nucleation sites, encouraging crystal growth. As for chemical changes and their operating conditions, we have chemical reactor. Chemical reactors are vessels where chemical reactions take place. They are used in various industries to produce a wide range of products. In petrochemicals, reactors crack hydrocarbons to produce fuels for vehicles. In the production of fertilizers, ammonia is synthesized in reactors where nitrogen and hydrogen combine under precise conditions to ensure a burgeoning global food supply. In the pharmaceutical industry, reactors synthesize life-saving drugs that epitomize the marriage of science and medicine. Researchers use innovative reactors designs to ensure sustainable energy solutions such as solar fuels and hydrogen production. In environmental energy engineering, reactors facilitate water purification by neutralizing pollutants and safeguarding aquatic ecosystems. Chemical reactors are where molecules collide and transform, standing as the heartbeats of innovation and shaping a myriad of scientific frontiers. The operating conditions can vary significantly, from minus 80 degrees Celsius for cryogenic reactions to over 1000 Celsius degrees for certain industrial processes. Pressures range from vacuum conditions to several hundred atmospheres. Residence time, indicating how long reactants stay inside the reactor, varies from milliseconds in rapid processes to delays in some biochemical reactions. Oxidation and corrosion. Oxidation is a process where an atom or molecule loses electrons. Corrosion is a type of oxidation that occurs when a metal reacts with its environment and undergoes a chemical change. Rusting is the most common type of corrosion, which is the formation of iron oxide on the surface of iron or steel. Corrosion can be prevented by coating, painting, galvanizing, or anodizing the metal surface. Corrosion and oxidation are both processes that involve the loss of electrons by a metal or metal atoms. However, corrosion is caused by the presence of water and other external agents, such as chemicals, microorganisms, or different metals. Oxidation is caused by the reaction of oxygen with a metal, either in air or water. Corrosion is a form of erosion or destruction of the metal, while oxidation is a change in the oxidation state of the metal. Corrosion can be defined as the deteriorating of materials by chemical processes. Of these, the most important by far is the electrochemical corrosion of metals. in which the oxidation process is facilitated by the presence of a suitable electron acceptor, sometimes referred to in corrosion science as depo- depolarizer. depolarizer. Electrochemical corrosion of metals occurs when electrons from atoms at the surface of the metal are transferred to a suitable electron acceptor or depolarizer. Water must be present to serve as a medium for the transport of ions. The most common depolarizers are oxygen, acids, and the cations of less active metals. Their operating conditions for corrosion are the presence of an electrolyte, an exposed metal surface, and an electron acceptor. Corrosion occurs when a metal continues to oxidize. Rusting is a specific example of corrosion, which occurs when iron or steel reacts with oxygen and water. Corrosion can be prevented by coating, painting, galvanizing, or anodizing the metal surface. Then we have polymerization. Polymerization is the alchemical fusion of small particles into intricate macromolecules, heralds the dawn of modern materials. Plastics, omnipresent in everyday life, owe their existence to the polymerization process, molding our world into a myriad of shapes and forms. The synthesis of synthetic fibers revolutionizing textiles epitomizes the versatility of polymerization, enabling the creation of durable and fashionable fabrics. In the pharmaceutical industry, polymerization builds biodegradable materials, offering sustainable alternatives to traditional plastics. Nanotechnology harnesses polymerization to engineer nanoparticles, promising innovative drug delivery systems and cutting-edge electronics. Tissue engineer, a beacon of regenerative medicine, employs a polymerization to craft scaffolds to nurture the growth of these tissues within the human body. Polymerization is a symphony of chemical bonds and innovation, empowers humanity to redefine materials and reshape the future. Operating conditions. Polymerization temperatures vary from 100 degrees Celsius for some specialty polymers to over 300 Celsius degrees for high temperature plastics. Pressure can range from atmospheric to several thousand atmospheres, influencing reaction rates and polymer properties. Initiators like peroxides break chemical bonds, starting the polymerization process. Monomer concentration affects polymer chain length, impacting material properties. Reaction can occur in solution, emulsion, or bulk phases, leading to different types of polymers. And this is all about physical and chemical processes.